All right, the next piece. These three expressions need to become synonymous in your mind. It needs to just be automatic. All right? It's just like the letter S. That symbol, the sound, and the name. We call this S, we don't call it W. We call this S, we don't call it J. So the name you call it, the symbol you write, and the sound it represents, those are so congealed in your mind, you sometimes don't even realize there actually are three different things there. Well, similarly, this needs to become automatic in your mind. The phrase one-to-one, a function is one-to-one, means the function passes the horizontal line test. So if we say it passes the horizontal line test, that means the function is one-to-one. If the function is one-to-one, that means it passes the horizontal line test. Passes the horizontal line test means it has an inverse function. If it has an inverse function, it passes the horizontal line test because it's one-to-one. If it's one-to-one, it has an inverse function. If it's inverse function, it's one-to-one. These are all the same. They have precisely the same meaning. It's different ways of saying the same thing. Different emphases are important in different contexts, and that's why we have different ways to emphasize this, or different ways to state it. But the function is one-to-one if the function passes the horizontal line test. Now there are several functions, you know this. Suppose we take the cube function. This is y equals x, or let's call it f of x equals x to the third. That's the cube function. Well, this function, what do we know about it? It clearly passes the horizontal line test. So this function passes the horizontal line test. That means it is a one-to-one function. If it's a one-to-one function, again, by the way, the abbreviation for one-to-one is 1-1. Anybody who knows what you're talking about knows that's the abbreviation. If they don't know this abbreviation means this, they don't know what you're talking about in the first place. So, one-to-one means the function passes the horizontal line test. And what that means is this function has an inverse function. There does exist an inverse function for this particular scenario. It turns out, in this particular case, the inverse function is the third root function. But all we're concerned with for now is a function is one-to-one, means it passes the horizontal line test, means it has an inverse function. If the function has an inverse function, it is one-to-one, it passes the horizontal line test. One specific case of that is the cube function. This is by no means the only instance of that, but this is one specific instance. All right? Now, another thing we know is this. Suppose suppose we know we have f and f inverse. Suppose we have a function and its inverse, and we know those are given. So we have a function and its inverse. All right? What do we know if function f contains the point a comma b, what do we know is on the point, or what it is on the function f inverse, the graph of f inverse? Well, we know this function needs to be, reverse the coordinates, b comma a. So any point that lies on the function f can be used to generate a point that lies on the function f inverse, and vice versa. Now let's think what that means. Suppose in this blue, we draw the cube function, f of x is x to the third. There are some points on this curve whose coordinates we know. We know 0, 0 lies on the function f. We know 1, 1. We know 2, 8. We know 3, 27. And as many as we would care to find. We also know -1, -1. We know -2, -8. We know -3, -27. And as many as those as we would care to find. But now we can use this principle to say that if we know, for example, suppose we know that 2, 8 lies on function f, as we do. then we know a point that lies on the inverse. We can figure out what the inverse function has to look like by interchanging these coordinates. And so if 2 comma 8 lies on F, that means 8 comma 2 must lie on the inverse. Look, if 1 comma 1 lies on the function, when you interchange those, well, when you interchange them, they stay the same. 0 comma 0, when you interchange it, it stays the same. -1, -1, it reverses to itself. But -2 comma -8 corresponds to -8, -2, which is down here. -27, -3 is way down here. Interchange these. 27 comma 3 is way over there off my board. And so it's not too hard to convince yourself that the graph of this thing, within the limits of my badly drawn picture, is something like that. Now, it might not be obvious, but when I draw this, it will be, I hope. This is the property that we're after. This is the key element. Because of this interchanging property, the following is true. As badly drawn as my picture is, if this is the line y equals x, if that's the line y equals x, these two curves, if were drawn well, these two curves would be mirror images of each other. Notice, on the red curve, as you get closer and closer, think of this as being the mirror. As you get closer and closer, I'm going to draw a better picture here. I'm just going to re-sketch this with a little bit more accuracy here. So there's the original function. There's the inverse. Here's the line y equals x. Think of this being the mirror. As you move closer to the mirror, your reflection moves closer to the mirror. As you touch the mirror, your reflection touches the mirror. As you go, Alice, through the looking glass, your image comes back out the looking glass. And then as your image gets closer, you get closer. And then when you touch, and so we can see that this is the mirror image. The blue curve and the red curve are mirror images reflected across this line, y equals x. Now, that happened in this scenario. It is not obvious, but it is in fact the case that if f of x, let's suppose this is the graph of f of x, that if you draw this diagonal line, the graph of the inverse is the mirror image. As you get further from the mirror, so does your reflection. As you get closer to the mirror, so does your reflection. You have the mirror image of this graph reflected across this line y equals x. Notice, if this is the point, let's suppose this has coordinates. It's a point on the y-axis. So this is maybe 0, comma, let's just pick a number out of the blue sky. That might be 0, comma 3. If we know that, then what must we also know about that point? Is it clear they must interchange? This is 3, comma 0. If I extend my picture down here, suppose we know this point is 0, comma -5, let's say. Then is it clear we also know the coordinates of that point, because the mirror image is you interchange the coordinates. This is -5, comma 0. So another principle is intercepts get exchanged. On the original curve, the y-intercept is at 3. On the inverse curve, the x-intercept is 3. On the original curve, the y-intercept is -5. On the inverse curve, the x-intercept is -5. Here, the y-intercept is -5. What was x becomes y. What was y becomes x. And that comes from the fact that the domain and the range switch places. What was x becomes y. What was y becomes x. And so that procedure is one of the principles we'll take forward. I've not proven any of this, but it is in fact the case that this is true, that because we're interchanging these coordinates to find these values on the inverse curve, one of the consequences of that is that the graph of a function and the graph of its inverse are mirror images across this diagonal line y equals x. And of course, yes, remember, if the curve touches the mirror, the inverse image must touch the mirror. If you get further and further away from the mirror, then your reflection must get further away from the mirror. as you get closer to the mirror, your reflection gets closer to the mirror. Just like your experience using the mirror. But that it will help you understand what's happening with the graphs of these functions. And so, if you are given, let's just say, that curve, you should be able roughly, just a rough crude approximation, you should be able to get a rough approximation of what the inverse is. One thing that will help is that distance must be the same as that distance. That sort of anchors it. And then all you're doing is, do you see how this looks like a vase? Right? It's just the mirror image. So this gets closer and then gets further away. So this is roughly the mirror image. That's as much accuracy as we're need of what we will do when we take this forward. So inverse functions. One of the properties is this reflection of the graph of the function and the graph of its inverse.